like you. They didn't miss anything. But now my clicker doesn't work. Hold on, what happened? So we have 5 volcano targets. They all are a little different in their unrest and their eruptive behavior. So Okmok, which has a caldera in Alaska, Cleveland, which is a classic stratocone and frequently degassing, Poas in Costa Rica, which has a crater lake, and Villarrica in Chile, which has an active lava lake in the crater. So all a little different, requiring different kinds of sensors. We've been hard at work for more than 5 years on this project. It started in November 2019. You remember what that felt like, and the COVID years after that. But after the COVID gap, in purple, we had 4 full field seasons with AVO in Alaska. And then we had a couple years. We were wrapping that up in Chile on Poas volcano of Sakuri in orange. And then in green is what we're planning now and into the future. We're hoping next January and February in Villarrica. So I'm going to say just a quick word about Poas and Villarrica, but then most of the talk on Alaska, because that's why we're here. Poas is a large shield volcano. We're up here at 8,000 or 9,000 feet. It has an active crater lake. And when we went to Sakuri and said, we'd like to work with you, we said, what would you like to do? How can we be helpful? And what keeps you up at night? And so Poas keeps them up at night. There are hundreds, if not 1,000 tourists who go up every day and try to take this picture from that spot on an active volcano in the national park. It's about 45 minutes from San Jose, the capital, and it's one of the #1 tourist destinations in Costa Rica. And this is what keeps them up at night. So Poas has been quite active. This is a thermal camera that we installed. We're watching an eruption that's partly phreatic, but also magmatic. And then here's the infrasound signal at the same time. And so when we started deploying our instruments in November is actually kind of when it started erupting. So that was interesting, but also challenging. And then over the 2 years, we've added substantially to Poas. We've added 5 new sites, mostly in the north where there weren't any. Lots of seismometers, this IR camera, a FlexGate magnetometer, added a GPS and MET station, soil CO2 probe that Connor will talk about, and a Starlink, a fully remotely worked Starlink to send data off by satellite. So at this point, Poas is probably the best monitored volcano in Costa Rica. We also had a fantastic opportunity, because it's so accessible, to bring people to the volcano and run field workshops. So these were where we invited people to bring crazy instruments and try them out for a week. And we did this 2 years in a row in 2024, and just last March in 2025, we've had over 60 scientists and students from 8 countries come, bringing 30 different types of instruments, including some examples. This is what a portable mass spectrometer looked like. We kind of joked, is this really portable if it weighs 80 pounds? But yes, it's a mass spectrometer in a Pelican case. But they set it up on the crater rim and measured noble gases and nitrogen and things that we don't normally measure. We had scientists looking for microbes in the plume and looking at different kinds of aerosols for health risks. And then another group installed a MEMS gravimeter, which is very exciting, and Connor's going to follow up on that. So this has been a lot of fun. I hope we do this again and consider being involved. All right, Villarrica, Lake Poas is a tourist destination in Chile. Lake Poas, we asked Sernahiamin, where would you like some collaboration? They said Villarrica. So it looks scary, but hundreds of tourists hike up this thing, wanting to look into the active lava lake in the crater. And Sernahiamin said that we really would like our instruments on the crater rim. So this is a challenge. This is what the crater rim of Villarrica looks like. So Connor was just there 3 weeks ago and took this picture. That's a helicopter. This is, we're looking at the crater rim. There's the crater inside with the active lava lake. So we're kind of looking at half the crater here. There's some flat areas where we're planning to put some instrumentation, which we fully realize might not survive with ballistics on it. Might have to put a station another place for the plume. Anyway, we're excited about this. It's not been done too often, and as Connor said, this is bold, but perhaps doable. And we're very happy to take advice from AVO folks about snowy installations. And Carlos Cardona is here from Cernapumene. There he is. Thank you, and very happy to exchange ideas as well. So look forward to that. All right, Okmok and Cleveland are targets in the Aleutians. Next door, volcanoes. Okmok has a large caldera in it, about a 10-kilometer caldera that erupted in BC 43 and is thought to have brought down in part the Roman Republic due to the hemispheric climate change that happened following that eruption. Jess Larson was involved in that study. And Jess also described the 2008 eruption, which is the most recent eruption in Okmok caldera that came out of that cone. Before 2021, which is when AVERT joined the work in Okmok, most of the data, there's quite a substantial network on Okmok, but all the data were going out through radio and then a repeater high on a mountain in Makushin and in Alaska and onward. And so that presented some challenges and frequent data outages. The current network now is also substantial, but we've added a lot to it. We actually doubled the GNSS network with instruments in the caldera, a new instrument, a couple new instruments, and there's now radio coverage in the caldera because Okmok inflates. And so the GNSS data is really, really critical. And then the VSAT that Max Enders showed before that sends data out by satellite now takes almost all the data on the island and point of source off the island by satellite. We added again some CO2 and temperature probes, the magnetometers. There's a new camera in the caldera and some nice photogrammetry. And Connor will tell you how to access all these data, which are open. Cleveland. There's amazing footage from a helicopter, so you can see what it looks like. It's actually not that different in scale from Villarrica. Cleveland is very active. It's a stratocone. It's almost always degassing. And it erupted almost every year between 2005 and 2020. Of course, when we put instruments on, then it stopped. But by those measures, it's one of the most active volcanoes in the US, really, having erupted almost every year for 15 years. And despite that, there were no instruments on Cleveland prior to 2014. So pretty newly worked on. Beautiful. Thank you. Did you do that, Connor? Yeah. So I think I've already said all this stuff. The eruptions are mostly a pancake dome that blows up and then rebuilds. And very remote. Max made that point. So these are the instruments that were there. There are really only two seismometers, infrasound, a camera in prior to 2022. Now it is considered monitored. So in order to be monitored, there must be 5 permanent seismometers. So we have that. That's an AVO policy. And a lot of firsts. These are the first continuous measurement of the magnetic field, the first dual IR visible camera, the first scanning DOAS. There's 2 of them now with continuous data measuring sulfur flux. Diana Roman was able to piggyback on a 11-station campaign seismic for 2 years. And then there had been no GNSS, and so 3 of those were installed. So it doesn't look like a lot, but a lot got done on Cleveland. And in fact, CLNE, this amazing site with 2 huts, is one of the most multi-parameter sites, if not the, definitely on a remote volcano in the US. So there's 7 different sensors: GNSS, seismic, magnetics, IR camera, visible camera, MET station, and scanning DOAS. So there's a lot going on at this site. Pretty exciting. Okay, so as a result of the 2 different volcano studies that we've done with AVO over the 4 or 5 years, we've helped to install up to 22 new sensors. They've been deployed. And again, a mandate from our project is that we hand everything over to the observatory when done. And so that handoff, as Max said, is pretty much complete. And there's a lot of new sensors on the volcanoes. Yes, I learned about what hundreds of batteries mean and solar panels and shipping and fuel. So there's a lot that goes into doing this work. The AVERT project, I just tallied, contribute, I think, over 700,000 in equipment and logistics, not including salaries. And so, yeah, as a consequence, there are some new kinds of instrumentation that are all open. I think I already mentioned all of these. Many are for the first time on any volcano in Alaska or even in the US. Okay, lessons learned. So the first lesson learned is like, it would be impossible to do any of this without AVO. So we could not go in there and do this, I don't think any organization. AVO has great relationships with federal agencies and native organizations that involve permitting, having the helicopter contracts, the boat contracts, safety protocols, just really vital. I couldn't see doing any of this without AVO. It takes a lot of communication. We had monthly, if not weekly, Zooms for years. When you work together in the field, it's very important to have clear statements of priorities, and that was not always easy. And then AVO just has a ton of expertise. So we purchased 7 new GNSS instruments, but Max Kaufman installed all of them. He's the expert. So we are really grateful for that. If you wanted to get involved, I mean, I'm not the right person to tell you, people from AVO could, but in our experience, piggybacking is a great thing. There's lots of examples from even back to margins and individual investigators like Diana and geoprisms of really successfully partnering with AVO, because if they're out there, it's a smaller increment to add if there's time and ability. I mean, this is not a great year, but hopefully in the future, there'll be good years to work together in the field again. AVO has an open real-time data culture. Most observatories do not. So that's actually huge. The data are largely open and real-time. There are open samples. There's an open sample repository. There's an immense amount of geological mapping for context. And well, I've found AVO has been very welcoming to collaborative, either analytical or modeling campaigns. So yeah, great lessons learned, I would say. All right, I just want to close with 2 slides. One is like, okay, we just put all these instruments out there. We kind of like Akhmak to erupt. Nothing like BC 43. We don't need to bring down the Mediterranean, but but the last eruption was 2008. The EI4 16-kilometer plume. It was a big eruption. It had very little, had really no precursory seismic activity except for 5 hours before. It's kind of crazy. It really is a record for shortest run-up for an eruption of any subduction zone volcano. That was a challenge, although it was inflating for a decade prior. So do you count that as run-up? So it's really interesting combination of signals. At the time, there was no functioning GNSS in the caldera months before the eruption. It was really painful. But in the months preceding, there were enough important signals. And then some recent work, I'm plugging Daniel Lee's poster with collaboration with Jess Larson, a bunch of other people looking at the 2008 samples. And Daniel found recent evidence that there was actually a fair amount of CO2 in this magma, and that the CO2 was exsolving as deep as 15 kilometers depth, which is where the seismic swarm was. So pretty interesting there. And that the crystal clocks show that there really was new magma coming in months before the eruption. And also the importance of getting the first ash sample out, which Jess Larson emphasized as well. So these are kind of lessons to think about of what to look for next. What can we see? Well, there's a new webcam in the caldera that could be important if a plume shows up. The CO2 degassing in the soil probe data looks really interesting. In some cases, it looks like it's gone along with seismic swarms. There could be magma influx. There could be magnetic field variations. All right, the telemetry is currently out. I'm very hoping this gets fixed this summer. So that would be great. And then I want to make a final plea. The big signal at Akhmak is inflation. It inflated, it erupted in 2008. And it's been inflating since, and is still inflating. And it's really one of the only quantitative successful hindcast models for the 2008 eruption, which could easily be flipped to a forecast model just based on inflation and failure criteria. This is Trish Gregg's group. She's not working on it. I would love someone to do that, to actually make a forecast of when Okmok's going to erupt next. So if someone's interested in that, Trish said she's happy to work on that model. And then for Cleveland, again, it erupted really frequently until 2020, but it certainly could again. There was a big seismic swarm in 2023 that was deep, 6-kilometer plume, dome destruction. There were no precursors, I think, to this eruption really, but that was before there were many instruments on the volcano, before it was really officially monitored. So we have a lot more to look at now. And in large part, it's the gas flux, because that plume is always chugging. And this is the amazing time series that's been developed by Christoph Kern and Skye Kushner. These are two different instruments measuring the sulfur flux in two different positions. And this is a multi-year record. This is incredible. And we don't really know what the ups and downs mean. Is it like the dome sealing? Is it new magma coming in? There's still a lot to understand about what's going on, but incredible data. There's data from space. There's new GNSS and seismic magnetic field data. It's all just sitting there. It's open. And I invite anybody to look at it and see what you find. That's the whole point of our project. So I'll end by just thanking all these people that were in the field in Alaska, and the leadership at AVO, which has been tremendous. And I'm happy to take any questions. Thank you. Did I go way over? Oh, okay. Or we can just have Connor go. Any questions? Yeah.
Thanks, Darren. This is amazing. So you talk about real-time data here. So where could we get all of the real-time data from from all of the sensors?
Connor's going to tell you. But a lot of it's on the Earth scope. It's on our own website. So yeah, that's what Connor's going to talk to you about. There's some of it has 10 or 20-minute latency. So it's not all strictly real time, but that saves a lot on power.
What was it like working with a private funding
I totally recommend it. You should all get one. You know, to this day, I have no idea how it happened. I mean, we are just really lucky. We were kind of right place, right time. The Moore Foundation doesn't really have calls for proposals. That we just happened to walk in and make a pitch when they had never funded anything on volcanoes. They'd helped fund Shake Alert. So they'd worked with the earthquake community. They worked with lots of other communities, but they said, oh, looks like something to do here in volcanoes. And seriously, they gave us $2.5 million in 2 months in a short proposal. So I hope they do more of that. But yeah, I wish I could tell you how it happened. Yeah. Yeah.
I'm really curious, and maybe, I don't know if you can answer this, about the magnetometer data, because I feel like I missed a memo that that's a thing.
I think we might be one of the first groups. There's a group in Chile, there's a group in Mexico, and again, Connor's going to talk about that. So it's a continuous fluxgate magnetometer. It's looking at the magnetic field, just the strength of the magnetic field. But it's very frontier measurements that Connor and Joe Biasi have been leading. Yeah. Leading up to you.